So if I grab up this terminal window over here, a completely separate window, a completely separate process, and I go cat test.txt, I want you to pay attention to this window over here. So if I hit enter, you'll notice, boom, file accessed. How sick is that? I just accessed this file from a completely separate process in a completely different terminal window, and our program over here was subscribed for that notification. Isn't that nuts? Hello everybody. Today we're taking a deeper look at INOTIFY. INOTIFY is a really interesting Linux kernel interface that lets your user space programs watch and listen to file system events. What do I mean by that? Well, let's say that a user or a process on my system opens or looks at a particular file. And let's just say I want to know about that. Well, INOTIFY will let you watch files on the file system with your applications, and your program can actually get updates about file system events. In fact, I believe the name INOTIFY, it actually comes from inode notify. If you're in the know, inodes are sort of the way that the Linux kernel and file system structure folders and such. So today we're going to be showing you a deeper look into INOTIFY, and to do that I have this demo program here. In fact, you might remember, if you're switched on, INOTIFY was actually one of the main components in by far the most popular video on my YouTube channel, where I demoed how you might use it in a practical application. But today we're going to be taking a deeper look into how it works and what you can actually do with it with the aid of this manual page right here, where it has a lot of detail about INOTIFY and what you can do with it. And we're going to be showing you some demo programs, and I've done some helper functions. So, not only are we going to be doing the INOTIFY system calls, but also I'm going to be showing you how you can build sort of a support structure around that to make it a little bit more useful. The first big concept when it comes to INOTIFY is the idea of a descriptor. INOTIFY uses two different kinds of descriptors. The first one is a file descriptor, and the second one is a watch descriptor. If you've never heard of a file descriptor before, you can think of it as an integer handle that represents a file or resource that you want to perform I/O operations on, so think reading or writing. As an example, I can ask the Linux kernel, hey, I want to open this file and I want to do something with it. And the kernel will go, okay, provided you have the permissions, here is an integer that represents that file. So when my program wants to perform I/O, like read or write to that file later on, I give the kernel the file descriptor that it gave me earlier, and it goes, okay, I know which file that you want to perform operations on. Here is the result of your call. And so kernel interfaces like INOTIFY and also EPOL and pipes and sockets, they all use file descriptors to represent resources. In this case, what we are getting a file descriptor to with INOTIFY is an event queue that we can read from. So what this event queue is a queue that holds all of our file system events. So we can read them in order. Let's say a bunch of file system events happen, our queue gets filled up, and our program can then read from that queue and grab all of the events. That's what we're using file descriptors for. And I'll show you this in action. So right here on the very first line of main, you see I define an integer called event_queue. This is going to be the file descriptor to that event queue I was telling you about before. And what you'll notice is that where I assign that is actually the result of INOTIFY init1. So let me go ahead and grab the man page for INOTIFY init, which is this one right here. And you can see what actually we do. If we call INOTIFY init, we return a file descriptor. And that file descriptor represents the event queue that INOTIFY is going to send all of its file system events to. So it's pretty important, and this is going to be one of the main constructs that we use in our program. I'll explain what these flags are as well. So with INOTIFY init1, we can pass it flags. You'll notice actually, if you go to this man page, there are two INOTIFY inits. There's an INOTIFY init and there's an INOTIFY init1. So which one should you use? Let's find out. So INOTIFY init initializes a new INOTIFY instance, that's what we want, and returns a file descriptor associated with the event queue. That's exactly what we expect. Now, if flags are 0, INOTIFY init is the same as INOTIFY init. What that means is essentially INOTIFY init1 was created to extend the functionality of INOTIFY without breaking this older interface. And you'll actually see that a lot in the Linux kernel interfaces. If you look around enough, you'll notice that there are a lot of like init1s and such that, or like system calls with 1 on the end because what they wanted to do was add functionality, but if they did that, it would break existing code that uses the old one. So they have INOTIFY init1 that takes these two flags. So in non-block, that's actually a really important one to know, because what essentially we have is with the standard way that INOTIFY works, if you give it 0, it's blocking. What that means is that your program will be waiting on events. In that time, it cannot do anything else. That thread, at least the thread that you're running this on, will be blocking, waiting for INOTIFY events. If you specify non-block, your program can do something else while it's waiting for INOTIFY stuff to come in. And that forms this first call here where we initialize our queue file descriptor. Flags I've actually set to 0 at the moment, so for this example, we're just going to be using the standard blocking INOTIFY interface because it's very easy to get an understanding of how it works. That's this first call here. Simply we have this, and we've got a very simple error handle because remember, if we looked at the man page, it returns a -1 on error. Our next thing over here is this event_d, which is the result of this call. So event_d is another integer. Remember I told you there are two kinds of descriptors that INOTIFY uses. The second one is a watch descriptor. Essentially, it's an INOTIFY construct that represents a unique ID associated with a file that you're watching. When we go ahead and add files to our INOTIFY watch, which you can see we do here. So for example, we have INOTIFY add watch, we have the event queue file descriptor, we have the name or the path of the file, which you'll see I've just done up here as a test, and we have these watch flags, which I'll explain in just a second. But what we get back is this watch descriptor, which is an integer value that represents the file that is being watched. It's not necessarily like an open file descriptor that we can do I/O on. It's just an ID, essentially, that we can use to map to our files that we are watching. For example, I could cache this and say, okay, well, I know that event D is associated with this file path here. So, of course, it doesn't store the file path in the INOTIFY instance. It stores this integer, and so I can use this integer as an ID to say, okay, it's this file. And I'll show you when I get to these helper libraries that I've made, I'll show you how you can actually use this watch descriptor in a useful way to map these things. Watch flags argument is actually really important here because it represents the kinds of events that we actually want to subscribe to and listen to. This is the main INOTIFY man page, and we scroll down and we'll find this section here, INOTIFY events. So this is a listing of all of the file system events we can essentially listen to. So things like access, metadata changed, file was open for writing and closed, the file was created, it was deleted, it was modified, it was moved. Things like this, when you're developing your application, you can go through this list and think about, okay, this is the event that I want to listen to, and you can put that in that flags argument to INOTIFY add watch, and it's actually over here, this mask argument here. So there are 3 arguments to INOTIFY add watch. There's the file descriptor that represents our event queue, there's the path to the file that you want to watch, and there's the mask, which represents those flags, those events that we want to listen to. So if I grab this back up here, you'll notice watch flags I've set to create, delete, access, close write, modify, move. So those are really the main big ones I can see that to give you a demo that's like really useful. Now, this is a bitmask. If you're not familiar with a bitmask, I'll go over it very basically. A bitmask is essentially, if I hover over this, you'll see it expands to 2048. This one expands to 2. This one exposes to 8. So they're all powers of 2. So a bitmask is essentially, if I have a row of bits, think about 1 byte, that's 8 bits, I can use every bit in that as a flag. So if I just toggle one of those bits to 1, that can represent a flag, and with this OR, we sort of combine them all together. So essentially, all this is doing is setting all of the individual bits in watch flags that creates our mask. So far, this has all been pretty straightforward. We've just initialized an INOTIFY instance, and we've added a file to the watch list. This is where things get a little bit more complicated. We actually have to read these events. And if you have a look at this man page for INOTIFY, at the bottom, they actually have an example program where they show you how you can do this. But I think this is maybe a little bit hard to follow, so I've tried to make my example a little bit easier to follow. But essentially, the big important thing is when you read from the INOTIFY event queue, what you get in return is this struct here. So this struct is an INOTIFY event. What it contains is your watch descriptor. So this is the watch descriptor that represents the file that was, that the event is for. It's got this mask, which is the event. So if you remember, we were looking at these events here. So the mask will tell you what the event was. It has this cookie. So I want you to consider this. What happens if we rename a file? Actually, it'll tell us. Cookie is a unique integer that connects related events. Currently, this is only used for rename events. So, for example, if I have a file that I rename that I'm watching, INOTIFY will generate a moved from event and it will generate a moved to event. Have a look at this. If we rename one of these, it'll do a moved from event for the first directory and a moved to event for the second directory and a moved self event for the file that you moved. These moved from and moved to events are connected by the cookie. So the cookie value is essentially saying this file originated over here and it's ended up over here. This is a link. So you can check or cache that link if you're interested in handling that kind of situation. The name field only seems to be populated if you're watching a directory. So in addition to individual files like we're watching in our example over here, you can also set it to watch directories, in which case this name field will be populated with the name of the file in that directory. Note that this name is not the full path to the file, but it is actually just the name of that file in that directory. So if you have the directory that's associated with the watch descriptor, then you can reconstruct the full path from the directory associated with the watch descriptor and the name of the file. Boring, 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 boring. Enough theory. How do we actually get these events into the right form and do something useful with them? First, we're going to look at the example from the man page because this is the official documentation and I feel like it's probably worth going over, even if I think that it's a little bit hard to follow. I'll try my best to explain it to you guys. Essentially, the first thing you have to do is get yourself a buffer to read this in, because remember, what we're actually doing is we're reading a file descriptor that contains these struct events. So if we have a look up here, you'll notice there's this static void handle events. And let's have a look at what they actually do. They've got a 4 kilobyte buffer, and what they do is they read the file descriptor, and this file descriptor they pass in here is the event queue. So you read the file descriptor into the buffer. Max size is obviously the size of the buffer. They have some basic error handling here. Let's assume that it is successful. So in fact, what you'll get is sometimes not just one event, you'll get multiple events. So what they actually have to do is go through this buffer. If you guys weren't aware, structs and in fact any data type you can represent as a buffer of unsigned 8-bit integers. So what they do here is they treat that struct as this uint8 buffer, they read it in, or I mean car, because car is a uint8, right? So they'll treat it as this unsigned integer, they'll read all of this raw data in, and then later on, you'll notice here we do this cast back to the INOTIFY event. So what's this for loop doing? I understand that. I understand that you can, have a struct represented as a buffer of bytes, and we can do a cast on that part of the buffer, and it'll actually treat it back as the struct that it is. But how do we actually get to that? This is where it gets a little bit complicated. This is a really, really difficult to follow thing here if you haven't looked at anything like this before. Essentially, we define in the initialization step of the for loop a character pointer that is at the start of the buffer. So that's the very start of the first byte that we've read. Our pointer in the increment step, the check step, is made sure that it is less than buffer plus size. So remember, when we use this read system call, it'll give us back the number of bytes that it read. So this is the maximum number of bytes that we have to be able to loop over. So this check just makes sure that pointer is not going to be exceeding the buffer plus the size. That's just pointer arithmetic there. You take the start pointer, you add the size, that's the maximum pointer that we'll be able to check. In the increment step of this loop, we take this pointer that we defined in the initialization step and we add the size of the INOTIFY event. And this is really important if you are using, pointers as raw bytes. When you want to go to the next one in your buffer, you add the size of that struct, and that's what they're doing here. Now, be careful. What you also have to do is add this event length, because if you remember, this struct over here also has this null terminated name field. And so what you'll have is the size of the name field, which is important because if I get back this struct, it's not just the size of this struct, but I also have to take into account the size of this name field as well. So that's essentially what we have here. If I can find it again, we are simply starting at the very start of our buffer. Every time we step our loop, we are adding the size of the struct before it plus the length of the struct before it, and we just simply do this cast. That's it. And then from here, we can go through and check our mask, see what the operation actually was. And then they do this thing here to print the watch directory. That's essentially how you read from the file descriptor, and you step through all of the INOTIFY events. And then in this bitmask logic here, that's where you can actually handle those events. I'll show you how I've done it in my example, and hopefully it'll make a bit more sense. After this read thing here, I've decided to go not for a sort of for loop paradigm, but I've gone for a while loop yield paradigm. So essentially what you do is you read from the event queue into the buffer, and then you pass to INOTIFY yield in this while loop structure here. So iEvent is very simply a pointer to an INOTIFY event struct, which of course is what we need. And INOTIFY yield, you pass it the buffer, the event, and the length. And INOTIFY yield is defined up here. So what we have is this buffer, event, and the length. You do a very simple check, is the event null? So this is the previous event, essentially. You pass it the previous event because remember we need the size of the previous event. Then the increment pointer is either the start of the buffer if it's null, so if you've never had a previous event before, or it's the pointer to the previous event plus the size of the INOTIFY event struct and the length of that event. So that's kind of what we saw in the man page. And then we just simply do this check. If it's greater than, if this pointer here is greater than buffer plus length, we return null. So essentially what this function yields, if you think about it, it will yield a valid INOTIFY event on success. And once you've reached the end of the INOTIFY events, it will yield null. So you can use it in this while loop like this with this assignment. While iEvent INOTIFY yield does not equal to null. And then you can simply go through and check. So enough of this boring stuff, let's do a demo. To recap really quickly, we talked about what INOTIFY init1 does. We talked about how to add a file. For example, we're going to be looking at this one here. We looked at how to add that to the watch list. We talked about how to read from this event queue into a buffer. And then I explained this simple function I have here that goes through and extracts this INOTIFY event struct, which contains all of the information about that event for us to use. All I've done here is I've built and I'm running this example program. And you'll see here, we're looking at /home/mdhof/test.txt. So it's now subscribed for all file system events that are associated with this file. So if I grab up this terminal window over here, a completely separate window, a completely separate process, and I go cat test.txt, I want you to pay attention to this window over here. So if I hit enter, you'll notice, boom, file accessed. How sick is that? I just accessed this file from a completely separate process in a completely different terminal window, and our program over here was subscribed for that notification. And then I goes, let's say BBBB, and I pipe it into test.txt. Check this out. File modified, file written, and then closed. How cool is that, guys? That's so sick. This file access stuff, as far as I can tell, after I write the file, I'm pretty sure it's my indexer, because my KDE's indexer indexes file content. So it's probably actually low-key using INOTIFY. The indexer is probably using INOTIFY, and it sees, oh, this was modified, so let me go and re-index it. Isn't that nuts? Okay guys, playtime's over. We've essentially just made a toy example application, but if you want to make syscalls actually useful, a lot of the times you'll find that you actually kind of need to do a bit of scaffolding around them. Because it's a Linux kernel interface, it doesn't necessarily provide you with everything a user space program might want. So for example, one major lacking feature of this original program here is if I want to watch multiple files, I need a way to associate a watch descriptor, like the one that we got here for this add watch, with the path. It's fairly simple because in this example, I've only got one file. So This file is obviously associated with this descriptor, but what if I want to watch multiple files? How would I go about, associating that when all INOTIFY gives me is a watch descriptor? And in fact, if we go and have a look at the man page again, I've pulled up this part of it right here, and you'll notice the INOTIFY API identifies events with watch descriptors. It is the application's responsibility to cache a mapping between descriptors and path names. So that's your job. That's your job. The kernel is not going to do that for you. You need to cache these path names and associate with them with a watch descriptor. And even more importantly, guys, you need to be able to update it if renamings affect the cached names. So that's why you might employ a helper library to assist you in doing that caching. Over here in this header file for INOTIFY helpers, I've defined a helper struct. What this does is it contains the watch descriptor associated with the file, it contains the event queue descriptor associated with that watch descriptor, and it contains the path, which is defined as path max over here by default, of that on the file system. So what that means is we have a way to cache the watch descriptor, the queue descriptor, and the file path all in one struct. If we go over to INOTIFY helpers, we sort of have this kind of paradigm. What we want is a list of these INOTIFY helpers, so an array of these INOTIFY helpers. Check out this init function I have for the initting the module. You give it the container, so this is an array of those helper structs, so it's an array of these ones. You have one for every file that you want to watch, and that's this size over here, and the queue descriptor that you want to associate with that container array. The first thing it'll do is initialize the queue descriptor to whatever queue descriptor you give it. So after you do INOTIFY init, you then pass it this queue descriptor that you want to be cached along with this watch descriptor. So then we set the watch descriptor to -1. So there's a free entry that's ready, available to be cached if the watch descriptor is -1. INOTIFY yield, I showed you that before, that hasn't changed, it works the same way. If I scroll down to this INOTIFY helper add, this is a wrapper for INOTIFY add watch that is also going to do the caching that we talked about. What we do here is we go through our container list, this container array, and we look for a free spot. So if you remember, if this watch descriptor is -1, that means we have a free spot in our sort of cache. And if we can't find one, we return an error. Then we try and add something to the watch. If it's -1, this will return -1 as well. Otherwise, we're going to copy the path, and that's essentially our caching done. Just a side note, now that I'm looking at this code again, this actually should be path length +1 because strlen does not include the null terminator. So actually maybe what I should do is do the +1 here and make sure. Probably should have used string copy here, but it is what it is. Always go back and double check your code because it's very easy to make mistakes like this. So we return this, and if it's a non-negative number, then it's going to be a success, and that's our cache. Similarly, we have INOTIFY helper rm, so it essentially goes through the cache and tries to find the path, and if it finds it, then it'll remove from the INOTIFY watch list. So we've essentially just wrapped INOTIFY rm watch, which by the way should be self-explanatory, and INOTIFY add watch to assist us with caching this file names and such. And of course, this is a very basic implementation. This is an array scan implementation. So you'll notice when we have this INOTIFY helper find, what we do is we scan the entire table and try and find the entry. Of course, you could speed this up with something like a hash map. And these are the files that we're going to watch. So we've got a couple of test text files, and then I'm also going to demo a directory to you guys because that's where things get interesting, and we haven't done that yet. So pretty standard watch flags. Here's our array of helpers, and we essentially init the queue just like normal. But instead of doing, our other stuff, we're going to init the helper library, and then we're going to use INOTIFY helper add when we loop through this files array over here. So we do INOTIFY helper add on all of these, and these are the files that we're going to watch. So we've got a couple of test text files, and then I'm also going to demo a directory to you guys because that's where things get interesting, and we haven't done that yet. So pretty standard watch flags. Here's our array of helpers, and we essentially init the queue just like normal, but instead of doing, our other stuff, we're going to init the helper library, and then we're going to use INOTIFY helper add when we loop through this files array over here. So we're going to do INOTIFY yield, and then we're going to do INOTIFY helper find. So what INOTIFY helper find does is this table scan based on the watch descriptor. You can see here, INOTIFY helper goes through all of these and checks the watch descriptor, and it'll give us back this container. The upshot of that is, once we have this container, we now have access to the path. So again, guys, the point of this is to cache watch descriptors versus file paths when we have multiple files. So you'll see down here, we can print the current path. So if length is 0, remember the length of the iEvent struct is 0 if it's a normal watch, but it will be non-zero if it's watching the directory. And because we're watching both normal files and a directory, we have to do this check. So if we're watching a normal file, we will use the cached path that INOTIFY helpers gave us. If it's a directory, we will print iEvent name, because that's the name of the file in the directory, and then we're caching the name of the directory with INOTIFY helpers. Then, of course, we just do this same thing. All right, y'all, I compiled and ran this program. We're going to test it watching all of these various files over here. So first things first, let's do the cat test. Say test3.txt, boom. Test3.txt, file accessed. Let me do into test1.txt, boom. We get the same stuff as we got before. Let's go and test desktop/demo. I actually changed it to desktop/demo. Touch test0.txt. You can see file created, file written and closed, test0.txt inside this directory. How cool is that? Let me do an ls. Let's try that. You'll see here we get the file. Maybe I should fix the logic there. File accessed. It should say folder accessed, but you know, that's just an if statement. Yeah, because we did a listing of this directory, obviously we accessed that directory. So now if I go ahead and make another file, and there you go. So this is really sick, guys. Maybe I can try doing rm this test, test 0. Oh, did you catch that? That was actually awesome. When I press tab for my tab completion, it actually accesses. That's actually so cool. I had no idea until I just tested that now. But yeah, if you do your tab completion, it'll access the directory, obviously, because it's going to complete. Anyway, that's actually really cool. Let's delete this one. File deleted. As you can see there, we're all working great. We're doing caching, we're doing everything. It's really, really nice. So that's a demo of how you can employ helpers around these syscalls. If you know their limitations, you can extend the functionality and make them really useful. That does it for this expose on INOTIFY. I want to do similar videos like this and the one I did on EPOL for other Linux kernel interfaces, so stay tuned. Cheers.